Okay, thanks. Thank you very much.
You're welcome.
It's nice to see. We still continue with the neutrino with Alejandro. Alejandro, if you want to share your
Yes.
screen. Okay.
Can you see it?
It's perfect. You have 10 minutes.
Okay, well, I want to start by showing you the main goal of this work in progress, which is a better understanding of neutrino emission of core collapsed massive stars as a function of new physical properties, mainly deduced from the need to extend the standard model of elementary particles, and to study the environmental conditions to set up some time delay between gravitational waves and neutrino emission. Well, given the nature of this talk concerning mainly with the jargon and the physics of elementary particles, I don't want to feed you with long calculation, and instead I want to outline the main ideas of this work. So I would like to start with some general but very important remarks for these works. The first one is that is a fact that gravitational waves and neutrino emissions not match, nor in time and nor in location of the source, as is showing these nice images by LIGO. The second one is that the time shifting between both emissions probably can be more or less understood. We consider the main mechanisms to produce neutrinos, which are the ones listed in here, per annihilation, photoproduction, plasma decay, and Bremsstrahlung on nuclei. For instance, in a very rough calculations for, let's say, mass of the neutrino electronic, which is parameterized with a theta parameter of 15 electron volts with that emission energy of 15 mega electron volts. And for a source located in our galaxy at a distance of, let's say, 10 kiloparsecs, the time delay between two signals detected on the Earth should be around 0.5 that parameter square seconds. And for extragalactic sources, the time delay increases like that showing on the screen. Now, if we take into account the most probably states of mass reported recently by the Katrine experiment, we can see that the time delay between two emissions must be around less than 10 to minus 2 seconds, which is not observed. And now, quite recently, it has been adopted another time window, considering also GW transients with high energy neutrinos emitted by gamma ray bursts, and this time window is about 1,000 seconds. But even so, not much between gravitational and neutrinos emission has been found. So there are some observational efforts trying to improve neutrino detector sensitivity, so decrease the number of expected events. And we need also to look at different energy windows to improve the number of detected neutrinos, which is some of them are very low. For instance, 3 in some of the cases, 3 neutrinos detected in some cases. And there are also theoretical efforts which try to look at new properties of neutrinos and environmental conditions sensible to produce this time shifting, and the intensity and time emission of neutrinos as a function of extended models beyond the standard model of particles. So, in fact, this work deals with these lattice aspects, intensity and time emission of neutrinos, and environmental conditions. So the radio of the energy emitted in neutrinos with respect to gravitational waves represents, in fact, a useful parameter to constrain the environment in those astrophysical events, and is also a great opportunity to confirm or to rule out compact binaries as neutrino sources, but also some of the models beyond the standard model, as they predict sometimes neutrino emissions after 2 weeks the initial event. In what follows, I promise not to bother you with a lot of maths, and instead I would like to present the physical and quite simple idea behind these calculations. So the standard evolution of massive stars changes with the addition of extra cooling, induced mainly by the existence of more internal degrees of freedom of neutrinos, such as an anomalous magnetic moment, an electric dipole moment, which increase the capability to carry away more energy. And these two aspects of the electromagnetic moments are the ones new in the calculations. So there are a lot of proposed extensions to the standard model. Let me show you some of them: the BL baryon lepton model, the T31 model, Rev-Dach symmetric model, simple little Higgs model, etc. And the main idea of all these models, of course, is to introduce essentially new particles, new mechanisms of annihilation, new ways to break or to establish symmetries, new coupling constants, etc., which in fact they look for solve more fundamental problems like the charge parity violation, the matter-antimatter symmetry, etc., etc. So just one example of what we are doing here is analyze the process of parallelization of electron and positons to produce a pair of neutrinos, electronic neutrinos, which is the most important part in the production of the energy in supernova or collapsed massive stars. But via the introduction of a new boson particle, the zeta prime particle, which is a very massive particle. Of course, the goal of this, the introduction of new particles, is more fundamental to solve the problems I already told you. So the procedure is quite standard, is to proceed to calculate the square transition amplitude. And then once we have this, we calculate the energy loss rates as a function of the novel properties with this. In fact, there is a dependence of the electromagnetic momentum and the mixing angles and the coupling constants and the mass of new particles predicted by the models. And then we compare the emission with the standard model for different densities and temperatures. So this can be done not quite straightforward, but is feasible. So what we get some kind of these nice results. I am showing you here some of the results for different models: T31 model, the left-right symmetric model, and the little Higgs model, which is the energy emitted by the massive star as a function of one parameter, which is the mixing angle beta. And you can see in the order of magnitude that there is a big difference between, for instance, the T31 model compared with the others two. And so for some of them who are really familiar with this kind of elementary particles, these are the gauge groups associated with each model, which is explored. And we can do with this. So I am not, of course, presenting here all the results, but because they are some of them are preliminary, but I would like to say that at the moment I have in kind of conclusions, but I have to say no. It's better to say some results to confirm, is that we have developed the analytical expression to study in detail the energy loss rates of our collapsed massive star in several models, and it allows to explore the emission of different conditions and densities and temperature. This analytical expression can be cast into numerical codes of massive stellar evolution, and so far the models are more sensible to changes in emissivity as the little Higgs model, which shows the hierarchy problem. And also preliminary is a star with masses between 8 and 20 solar masses, seems to be sensitive to the neutrino magnetic momentum, but not so for the electric dipole moment. Thanks, and please questions or answers if you want. Thank you.
Well, thank you. It's a nice picture.
Yes.
If you have questions or comments, we are perfectly in time, so we have time for 1 or 2 questions. There is no problem. Don't hesitate. Huh? No, it looks very clear. Huh? I have no question personally.
Okay.
Okay, thank you very much, Alejandro.
Okay.
It's very kind. And we have now